Okay, so what I would like to talk about today is work that has been published recently this year, and I've done this work with the collaborators that are listed at the bottom left of the screen. And in this work, we have targeted massive stars in the Small Magellanic Cloud. So here's a picture of it. And the Small Magellanic Cloud is a unique environment because it is metal poor. It is nearby enough such that we can somewhat comfortably study individually stars. And also it's currently forming stars, which means that the massive stars have not died out. And therefore, here we are looking at a really unique stepping stone to study massive stars in the early universe. And of course, given that we're at the 5th day of this conference, I don't have to explain to you the importance of massive stars in the early universe because they are essential to understand, for example, long-duration gamma-ray bursts, superluminous supernovae, black-hole mergers, ionizing radiation, etc. I probably forgot to mention a number of important things. So what we wanted to do in this work is deliver, this is the rather ambitious goal, is to deliver a complete census of bright stars in the Small Magellanic Cloud. To the right, I know I mentioned a few previous works who have attempted to do the same. And the way we are trying to do this is use data that is currently available and try, because people have kept studying stars in the SMC and more and more data has been collected. And what we tried in this work is to use it as much as we could, as well as we could to achieve our goal. And the backbone of this work is a spectral type catalog from Bananos et al. From 2010 that contains over 5,000 stars, mainly massive stars, mainly OB stars. So what we use this for is to get an effective temperature for our stars. So for example, there is an 09 dwarf star in the B10 catalog, and we convert this with a spectral type temperature relation to an effective temperature. Then we also cross-correlate the catalog with the Gaia data. And by combining the effective temperature, a bolometric correction, and observed G magnitude, we can obtain an estimate for the luminosity of the star. Also, we can use the Gaia data for a completeness estimate and also to do foreground cleaning. And finally, in the years, people have observed subsamples of massive stars with dedicated atmosphere analysis studies. And these we can use to see if our estimates for the temperatures and the luminosities make sense. All right, so what I will do right now is fill this Hertzsprung-Russell diagram. So the tracks are from work that we have published 2 years ago. And before we start, one thing, I'm not sure the arrow at the top of the screen is well visible, but there is a 1/2 TMS line right here that is rather close to the ZAMS, and that is where our models reside once they are halfway their main sequence lifetime. So we would expect to observe a lot of stars close to the 0-age main sequence. However, these are the results. So these are all the sources in the B10 catalog that are luminous enough to end up in the Hertzsprung-Russell diagram. And before I'm going to discuss this, I would like to add a few more stars. So for red supergiants and for Wolf-Rayet stars, which are thought to be rather complete in the SMC, we don't think that we can do better with this method in terms of number and accuracy. So what we do is just add the data from these studies from Davies and Potsdam to the HRD. And then, a few more tests before we start to discuss the HRD. One thing is that, as promised, I will check if the temperatures and luminosities make sense that we use with our method. So for a subset of the stars in the B10 catalog, there are available estimates for the temperature and the luminosity. For example, with the D19 is definite all 2019, R19 is Ramachandran et al. 2019, Mokim et al. 2006, and a few others. And what we see is that while there are individual differences, of course, we are not doing extremely bad with the estimates for the temperature and the luminosity. And also there are no real systematic errors with a systematic overestimate of luminosity or temperature and such. Okay, and another important aspect, of course, is the completeness of our Hertzsprung-Russell diagram. And for this, we have used Gaia. So the Gaia, and we also have a data set where we didn't cross-correlate Gaia with B10, but just downloaded the raw relevant Gaia data. And what we're showing here is again an HRD, but the only difference is that the temperature is obtained using the Gaia color and not a spectral type, because we don't have that for all the Gaia sources. And this we use to estimate the completeness. So, for example, a black dot is a source that is only in the Gaia catalog, and a red dot with a black edge is a source that is both in the Gaia and the B10 catalog, which is the backbone of this work. And what we see, so we just count the sources in different luminosity intervals that are separated by the dashed lines. And what we find is that at the top end, we are rather complete, or the B10 catalog is rather complete, about 80%. And this gradually decreases to about 40% completeness at log L is 4.5-ish. So yeah, we're not complete, but especially at the top end, the B10 catalog is also not doing very bad at all. And as a brief sanity check, we check how well the luminosities correlate when we calculate them using just the photometry from Gaia or the other method, which can be spectral type plus Gaia magnitude, or VSS stands for various spectroscopic surveys, which are, for example, Dufton et al. 2019, etc. And what we see is that, as can be expected, there is significant scatter because it is very difficult to obtain the luminosity of a blue massive star with photometry. But for our purposes, it is not too bad either, because there is a very clear correlation between photometric luminosity and luminosity as determined by methods that we would deem more reliable. Good, then we can finally start discussing features in our Hertzsprung-Russell diagram. And the first feature is that there are not many bright stars. So with, for example, the blue line is the 40 solar mass track. And in an entire galaxy, there are not that many stars above this track, of the order of 25. And we can compare that with some other estimates. For example, in the entire HRD, we have around 800 stars. And for constant star formation, as Salpeter IMF, we would expect instead that 75 stars would lie above this 40 solar mass track. And if we use the same approximations, but assume a canonical star formation rate of 0.05 solar masses per year, we would expect even more bright stars. And as you might be aware, a dedicated effort has taken place to study massive stars in the twin brother of the SMC, the LMC, in particular in the Tarantula Nebula. And I'm going to do a quick comparison. So I use the same y-axis scale in both plots, but the compilation of Bestenleiner et al. 2020 just goes to a lot higher luminosities. And if you count, for example, stars in the subregion of the LMC, there are 27 that are above the 100 solar mass track.
2 minutes.
We just have, yeah, thank you, John. Well, we just have one. So there is so in the subregion of LMC alone, there are much more bright stars, which, is a stands out quite a lot. And secondly, the second feature that I'd like to discuss is the stars that are in the first half of their main sequence lifetime. And as you can see in this plot, there are almost no stars to the left of the half main sequence line, where half of the stars would be expected to reside. This number is well below 10%. So yeah, this is an even more surprising feature that we certainly hadn't expected when we undertook this study. And let's discuss a few possible explanations for both features. So it could be that the star formation history is special, meaning that between 5 and 3 million years ago, the star formation has suddenly basically stopped in the entire galaxy, which could naively explain both features. But one suspicious thing is that if you have listened to Gonzalo Holgado's talk, something similar, a lack of young stars, is observed in the Milky Way, and that these two disconnected environments have the same exact star formation history that needs to be tweaked a lot. Sounds suspicious. A second explanation is embedding or obscuring behind birth clouds. And while we do not have the observations to show that this takes place, but I would like to point at a study in the Carina Nebula, a very recent study where all 5 stars, so very early O stars, very bright stars, were observed with the K-band spectroscopy, and these had an extinction of about 10, so they would never end up in our Hertzsprung-Russell diagram with such a high extinction. I don't have time to talk about if it's likely that our sample is biased or not, but we have thought about this hard, and we don't think so, or not to the extent to change our conclusions. But as long as the stars are not detected, we cannot provide a final answer to why we see these two features. Let me emphasize that. So the takeaway message is that we provide a hopefully nearly complete overview of massive stars more in excess of 15 solar masses in the SMC. And surprisingly, half of the stars are missing. We found a dearth of bright and young stars. And the last thing I wanted to say is that if the explanation is not the star formation history, then this should have implications for the amount of ionizing photons and the way the IMF appears if these stars are there, but I do not manifest them as such. That is it. Thank you very much.